Today, the first thing we're going to talk about is setting equations equal to 0, just solving equations. Because as soon as you finish with your related rates, which you started right after test 2, the next subject is going to be sketching graphs. And to do that, you're going to take a derivative, set it equal to 0, take a second derivative, set it equal to 0. So it's the setting it equal to 0 that is hard, because finding the derivatives you've had lots of practice with already. So let's just practice that. So I've started with a quotient rule function. So y primed would be low, high, low, high. The quotient rule will try. So low, d high, less high, d low, all over low times low. Now, when we weren't setting them equal to 0, you were always told, oh, you don't need to simplify. But if you're going to have to set it equal to 0, you're going to want to simplify it as much as you possibly can. So I look at the top row here, and I have a bunch of x plus 3 to a powers. And I have an x plus 3 to a power down below. So I look for the smallest power, and I'm going to factor that out. So I'm left with an x plus 3 with that first term times 2 minus 2x times 5, and this x plus 3 is now sitting out in front.
Can I pause you for a second? Can you hear me?
So now I can cancel this. I have 4 x plus 3's up here. I'll get rid of 4 of the x plus 3's down there and just have 6 of them.
Professor, can you hear me?
So now I'm going to simplify this numerator. And then 2 minus 10 gives me minus 8x plus 6 over x plus 3 to the 6th power. I cannot hear you. I'm sorry. Do you have a question?
I did. Can you hear? You still can't hear me?
Oh, let me turn my volume up. I can barely hear something there. Let's see.
Can you hear me now?
Okay, I've got it on max. Try again.
Can you hear me now?
Barely. So
Still no?
what's your question?
Let me, I think if I shut off that. How about now? Can you hear me now?
That's better. Yes.
Okay, I guess they added some noise suppression on. I wanted to stop you earlier, but I guess the mic wasn't working. At the third line where you factored out the x plus 3 to the 4th, I'm kind of confused how that works. And this just might be something I'm missing on the algebra portion, but if you put that to each term, wouldn't the 2 get it factored separately? I'm kind of confused how that works.
Okay.
You just treat that as one term in the.
So this is 1 unit and this is 1 unit because they have the minus sign between them. Right. So I have 5 x plus 3's up here and I have 4 x plus 3's over here. Right. So I'm going to take 4 x plus 3's and put it out front. Then I'm left with just one of the x plus 3's and the 2. That's all 1 unit. 2 doesn't have its own x plus 3's. It's just sharing those. And then 2x and 5 are sharing these x plus 3's. So they don't have any left.
So if you were to reverse it back, you wouldn't FOIL, right? I'm stuck in the mindset that you would take that beginning term or set. What's the right term for that?
Yeah, you would not FOIL this. This would be a distribute. So this term would get an x plus 3 to the 4th power, and that term would get an x plus 3 to the 4th power.
Okay. Now that's clear now. Thank you. I'm sorry.
You're welcome. No, that's you're supposed to stop me when you have a question, so that was good.
The mic's all good now, though?
Yes, I can hear you now.
I was talking to you the whole time. I feel bad now. I'm sorry.
That's okay. I had my volume turned down from when I had that loud rock and roll music on. Okay, so now we're good. We have x to the plus 3 to the 6th in the denominator, and we've simplified stuff. So far, so good, Edwin?
Yep, looks good.
Okay, so we want to know when derivatives are equal to 0 and when they're undefined. If you have a quotient, they're going to be equal to 0 when the numerator is equal to 0. So minus 8x plus 6 is equal to 0. So let's just call this 8x. We'll add that to each side. X is equal to 3 over 4, 6 over 8, or 3 over 4. So that's where the 0 is. Now, this thing is going to be undefined when the denominator is equal to 0. And the only way x plus 3 to the 6th is equal to 0 is if x plus 3 is 0. So if x is negative 3. Next, we want to know when the second derivative is 0 and when it's undefined. So let's just write down the simplified version of the first derivative.
So does that mean that it's there's an asymptote there when it?
Yeah, there is an asymptote there, and you can tell that from the original equation.
And what's the trick to knowing if it's horizontal or vertical?
You have vertical asymptotes when denominators are equal to 0. Okay. You have horizontal asymptotes if you look at the limit as x approaches infinity.
Okay, but it's not the opposite if the numerator is 0?
No, the numerator is 0 is where you cross the x-axis.
Okay.
So now I have to sing that song again. Low, high, the quotient rule we'll try. We have low, d high, less high, d low, and I'm going to run out of room. 6 times x plus 3 to the 5th power, all over low times low. So x plus 3, and 6 times 2 is 12. So we're going to do that same little trick again. That's why I chose this problem, because that little trick works quite often. We have an x plus 3 to the 6th power and x plus 3 to the 5th power. So I'm going to pull out x plus 3 to the 5th power. Now from this first little unit here, I'm left with an x plus 3 and a minus 8. From the second little unit here, I'm left with the minus 8x plus 6 and a 6. And down below, nothing has happened. But that just makes my life a little simpler, because this can go away, and that is now to the 7th power. Now, distribute that 8, minus 8x minus 24 And let's distribute a -6 through here because I have a negative here and a 6. So a negative times a negative gives me a positive. And then a negative times, a negative times a positive gives me minus 36. And all of that is still over x plus 3 to the 7th power.
Is that 48x?
Yes, thank you.
Sorry, I got confused.
Oh, yeah, thank you. No, that was just a little typo, so to speak. Let's see, here we go. There. And now let's combine stuff. I have a minus 8x plus 48x. That gives me 40x. And then minus gives me minus 60 over x plus 3 to the 7th power. The y double primed is equal to 0 when the numerator is equal to 0. So when 40x is equal to 60, so when x is equal to 60 over 40, which is 3/2. Second derivative is undefined. When x plus 3 to the 7th is equal to 0, which is the same place as the derivative was equal to 0, x equals -3. So your second derivative, your first derivative, and your function don't exist when x is equal to -3. Second derivative is 0 at 3/2. And the first derivative is equal to 0 at 3/4.
What would that look like on a graph for double prime?
For double prime,
like
what is it?
If you were given a graph with it and it was, I don't know, if you could use it to kind of hint and double check your work, what would show up at that point?
This would be, what you would do is make a sign chart and figure out where it's positive and negative. Well, this denominator is always going to be positive. This numerator, this is a line with negative slope, which means it's going to be positive for numbers less than 3/4 and negative for numbers bigger than 3/4. So if you have a number less than 3/4, this graph will be concave up. And if you have a number less than 3/4, it will be concave down, because it'll be concave up when the second derivative is positive, concave down when it's negative. You're probably going to learn that next week.
Gotcha. Thank you.
Yeah. That's the whole purpose in this, is to get you ready for next week when you're going to be making those sign charts and figuring out how to graph things. Because when your first derivative is positive, that means your tangent lines are positive, so it's increasing. When your first derivative is negative, your tangent lines are negative, so it's decreasing. All righty, let's look at the next one. Y is equal to square root of 1 minus x squared. And of course, I'm going to write that as 1 minus x squared to the 1/2 power, because that makes it way easier for me to take the derivative of it. 1/2 falls down. Subtract 1 from the exponent. And then take the derivative of the inside function, 2x. Again, I'm going to want to simplify this as much as I can because I'm going to set it equal to 0. So first, that 2 can cancel with that 2. Negative exponent means I really live below the fraction bar. So I'll put a minus x up top, and then I have a square root of 1 minus x squared down below. So this y primed is equal to 0 when the numerator is equal to 0. So when x is 0. Y primed is undefined when square root of 1 minus x squared is equal to 0. So when 1 minus x squared is equal to 0. So when x squared is equal to 1. So when x is plus or minus the square root of 1. So one place where the derivative is 0, and two places where the derivative doesn't exist. Let's look at the second derivative. And now we're back to low, high, low, high. The quotient rule we'll try. So it's low, d high, less high, d low. So 1/2 of 1 minus x squared to the minus 1/2 times minus 2x. All of that over low times low. So I'm going to simplify this sum, make it look a little friendlier. I'll just put a negative sign in front of 1 minus x squared right there. I have x here, that 2 can cancel with that 2. I have a minus times a minus, which would be positive, but I have a minus here, so I still have a minus sign hanging out. X squared sitting on top, and then again, this tells me, hey, I'm on the wrong side of the fraction bar. I should be under here. And then the square root squared is just 1 minus x squared. So that's a lot more compact. But I really don't like having a fraction on the top of my fraction. That offends me. So I'm going to get rid of that by multiplying numerator and denominator by 1 minus x squared, square root. That way I can cancel that away and life will be good. When I multiply square root of 1 minus x squared times square root of 1 minus x squared, that square root disappears as if by magic, and I'm left with 1 minus x squared. This one cancels with that one, and I have minus x squared left. Down below, I have 1 minus x squared times the square root of 1 minus x squared. So far, so good? So minus minus gives me plus x squared minus x squared. All of that over, and I'm going to be fancy and write this as 1 minus x squared. This is the first power. This is the 1/2 power. So the 3/2 power. X squared minus x squared goes away. So my second derivative is equal to 0 when the numerator equals 0. That will never ever happen. -1 is never going to equal to 0 no matter what. And it doesn't exist the same place as the first derivative didn't exist. Undefined. when 1 minus x squared equals 0. So x equals plus or minus 1. Questions? Okay, we'll do one with a log. Derivative of log, whatever I'm logging is going to go on the bottom of the fraction bar, and the derivative of what I'm logging goes on top of the fraction bar. Easy peasy. Y primed is equal to 0 when 2x is equal to 0, so when x is equal to 0. It's undefined when the denominator equals 0. And that will never ever happen, not in the real world, because that would require x squared to be equal to -5, and that's not going to happen unless we invite imaginary numbers to the party, and they are not invited to our party. So we'll look at the second derivative, low d high less high d low all over low times low. Again, because we're setting it equal to 0, we're going to simplify as much as we possibly can. So 2x squared plus 10 minus 2 times 2 is 4, x times x is x squared. All of that over x squared plus 5 squared. So 2 minus 4 is minus 2x squared plus 10. And x squared plus 5 squared. Second derivative is equal to 0 when -2x squared plus 10, the numerator, is equal to 0. So when -2, let's make it positive. I like positive numbers, so 2x squared is equal to 10. So when x squared is equal to 5, so plus or minus square root of 5. It's going to be undefined when the denominator is equal to 0, and that's never. Not in the real world. That one wasn't bad at all. Now let's look at this ugly one with the product rule in it. So my derivative is first times the derivative of second plus second times the derivative of first. Making it look a little better, x to the 2/3. That negative exponent, again, means I'm on the wrong side of the fraction bar. So 2 and x minus 3 live on top of the fraction bar, and 3 and x to the minus 1/3 live on the bottom of the fraction bar. If you only had to set the first derivative equal to 0, you could go ahead and do that now. But I'm going to go ahead and combine this into one handy dandy unit because it will make our life a whole lot easier when we get to the second derivative. So let's find a common denominator, and that should not be negative now that I put it down below. It should be a positive 1/3. This is my common denominator. So I need to multiply 3x to the 1/3 times x to the 2/3, 3x to the 1/3 plus, I think I'll go ahead and distribute that while I'm at it. Now I have a common denominator. I just have to combine numerators. Oh, and I'm really happy because x to the 1/3 times x to the 2/3 means I add exponents, and that just gives me 3x. So 3 plus 2 is 5x minus 6 over 3x to the 1/3 power. Now I'm ready to figure out when the derivative is equal to 0. So when 5x is equal to 6, when x is 6 over 5, and then y primed is undefined. When 3x to the 1/3 equals 0, and that happens when x is equal to 0. Now we'll look at the second derivative. And I'm really glad that I simplified it into this instead of dealing with that. I'm going to go ahead and write it down again. It's low, d high, less high, d low, all over low times low. Now I'm once again going to simplify stuff. 3 times 5 gives me 15x to the 1/3 minus 5x minus 6 is on the top of the fraction bar, and 3x to the 2/3 is on the bottom of the fraction bar. And down below, I'm going to give that 2 to the 9 to the 3 and square it, and then x to the 2/3. And doggone it, I've got another fraction on top of a fraction, and as you know, that offends me. So I'll multiply by 3x to the 2/3 over 3x to the 2/3, because I can do that because multiplying by 1 is always legal. That will cancel with that. I have 3 times 15, which gives me 45, and x to the 1/3 times x to the 2/3 gives me just an x. Yay! I have 3, let's see, minus, oh, that cancels with that, so I'm left with just minus 5x minus 6.
Can I ask you a question?
Yes.
So I understand that when you flip, or when you change the x denominator to the numerator, it changes the power sign, right?
Mm-hmm.
But I am confused on how that works with in the second part where it's the 5x minus 6 over 3x to the 2/3.
So this one just cancels with that one.
Yeah, but how does it become just positive 2/3?
I multiplied both. This became positive because I brought it down to the bottom.
Yeah,
and then I chose this so that that would cancel. That was my whole reason for multiplying by that.
Yeah, I'm just working through because I would have got this wrong on the test for sure. And the reason why is I imagine on the numerator on the first part where it says 5x minus 6, I imagine imaginary over 1, and then I just imagine that you just multiply the two fractions, and then the 3x to the negative 2/3 just goes underneath times 1. So I don't. That's what's confusing me, is how that becomes a positive. Because I thought it was you had to switch them.
Okay, so let me grab another.
On the algebra of that.
Yeah. So we have 5x minus 6 times 1/3 x to the negative 2/3. So 5x over 1, that's fine. That's a legal thing to do. That would be 1/3. And then this negative exponent, I'm putting it under the fraction bar. And when you put it under the fraction bar, it becomes a positive exponent.
Okay. Now that's what I was missing. So that's technically, it's not 3. Yeah, that would make sense now. It would have to be 1 over 3x to the negative 2/3, right?
It's 1 over 3x. And if you bring the 2/3 down here, it becomes a positive 2/3.
Right. So you would need to have that whole portion underneath 1 for it to be what I'm thinking. Right?
Yes. You're thinking of 1 over 3x to the negative 2/3.
So in that case, you would just flip it to the top, right? And then it would become positive?
Yes.
Okay.
Yeah.
All right. Totally clarified it. Sorry.
Awesome. That's good. I'm glad we figured out where the sticky point was. Yes. Exponents only apply to the thing they're right next to. And a negative exponent, no matter where it is, means, hey, I'm on the wrong side of the fraction bar.
Okay.
Now, let's go back here where I'm really happy because I get to cancel, and canceling brings me joy. That canceled away with that. I have 3 times 9 is 27. I have x to the 2/3 times x to the 2/3 gives me x to the 4/3. And now 45 minus 5 gives me 40x, and minus minus gives me plus 6 over 27x to the 4/3. See if I got the same thing. Somehow I lost something somewhere. Let's see. Five times 3. 3 times 5, that gives me the 15. And how did I make that into a 45? Because I multiplied by 3x to the 2/3. And let's see. That's because I lost this 3 here. When I did high, D low, I lost my 3. So that 3 should not be there. So that 3 shouldn't be there. That 3 shouldn't be there. That should be 15. That should be 15. That should still be a 9. And now we have 15 minus 5 is 10x plus 6 over 9x to the 4/3. Hate it when I make mistakes. So now this is going to be equal to 0 when 10x plus 6 is equal to 0. So when 10x is equal to 6, so when x is equal to 6 over 10, or negative 3/5, because I needed to subtract 6 from each side. And it's undefined when x is equal to 0. Questions? Okay. Now this one is kind of like that one. It's kind of like what that one would look like if we had distributed that x to the 2/3 throughout the parentheses instead of using the product rule. So we're going to get similar kind of results. It's way easier to take the derivative of, though. So 2/3 falls down. 2/3 times 5 is 10/3, x to the subtract 1 from the exponent. Stop me when I make mistakes. 2 times 5 again is 10 over 3. Subtract 1 from the exponent. 5/3 minus 3/3 is 2/3. Now, again, if all you had to do was set it equal to 0, you could do that right here. Do 10 over 3x to the 1/3 minus 10x to the 2/3 over 3. And you could just set that equal to 0 and then cross multiply. But we know what's coming. We know we're going to have to do the second derivative, so let's go ahead and combine it into one handy dandy unit. So my common denominator is 3x to the 1/3 power. I just need a x to the 1/3 power attached to this guy. So I have 10 over 3x to the 1/3 minus 10 x to the 2/3 times x to the 1/3 gives me x to the 2/3 plus 1/3, which is just x over 3x to the 1/3, and one handy dandy unit. That's not so bad. That's not bad at all. So y primed is equal to 0. When 10 minus 10x is equal to 0. When 10x is 10. When x is 1. And y primed is undefined at 0. Now, let's see if I can do the second derivative correctly this time. Low. And I'm going to go ahead and turn my board sideways because I write too big. Low, d high, less high, d low, don't lose my 3. So 3 times 1/3 falls down, x to the minus 2/3. all over 3x to the 1/3 squared. So let's simplify stuff. I have negative 10 times 3. And that should be 1/3. Minus, I'm going to put 10 minus 10x on top. That 3 cancels with that 3. And x to the 2/3 comes down below. All of that is living on top of 9x to the 2/3. Did I make it so far so good?
So far, so good.
Cool. Get rid of that fraction over a fraction. Yay, 2/3 times x to the 1/3 gives me a plain old x. Cancel, cancel. 10 minus 10x. And down below, I have 9x to the 4/3. So minus 30x minus 10 minus minus gives me plus 10x. So this is going to be equal to 0 when the numerator is equal to 0. So minus 20x is 10, so x is minus 10 over 20, or minus 1/2, and it's undefined when x equals 0. So the purpose of this one and the previous one was, again, to help you get used to multiplying numerator and denominator by something to get rid of a fraction over a fraction. Those little tips and tricks come back over and over again. I think we got one more, because we can't have a day without an exponential function. Low, high, the quotient rule will try. It's low d high. Nice thing about e to the x, the derivative is e to the x. Less high, d low, all over low times low. And this one is to help you remember how to solve exponential equations, because you may not have done that in a while. Low times low. So let's distribute. E to the x times 1. E to the x times e to the x is e to the 2x. Minus minus is plus, e to the 2x over 1 minus e to the x squared. Oh, that simplifies. So I just have e to the x sitting on top of 1 minus e to the x squared. So this is going to be equal to 0 when e to the x is equal to 0. When is e to the x equal to 0? E to the x looks like this. It lives completely above the x-axis. It has a horizontal asymptote at x equals 0, at y equals 0, excuse me. but it never touches it. It tries really hard, but it never gets there. So this has no solution. So has no zeros. It's undefined when the denominator is equal to 0. So 1 minus e to the x squared equals 0, which only happens if 1 minus e to the x is equal to 0, which only happens if e to the x is equal to 1. Now, maybe you remember that that only happens when x is equal to 0, or maybe you do the natural log of both sides. Natural log of e to the x is equal to the natural log of 1. Natural log of e to the x is x. Natural log of 1 is 0. So this is undefined at 0. Second derivative. Low d high less high d low. So 2 falls down. Put some parentheses around that so I'm less confused. Subtract 1 from the exponent, multiply by the derivative of the inside function. All of that is over 1 minus e to the x squared, which is the 4th power. Well, oh, we have 1 minus e to the x here and 1 minus e to the x here. So we can do that little trick that we learned in problem number 1 of factoring out a 1 minus e to the x. So I still have a 1 minus e to the x in this first little partnership here, and I have an e to the x. This e to the x is gone from that partnership. I have minus, so plus 2 e to the x times e to the x is e to the 2x. Well, that can just go away, and that becomes a 3rd power. And that's a lot simpler. Life's getting better. So I have e to the x minus e to the 2x plus 2e to the 2x, all of that over 1 minus e to the x to the 3rd power. E to the x minus plus, so that gives me plus e to the 2x over 1 minus e to the x cubed. Whew. So this is equal to 0 if e to the x plus e to the 2x is equal to 0, which is equal to 0 if e to the x times 1 plus e to the x is equal to 0. I just factored an e to the x out, so I could use the 0 factor property. If this times that is equal to 0, then either this has to be 0 or that has to be 0. Well, we already know that ain't happening. E to the x equals -1. E to the x looks like this. It lives completely above the x-axis, so that ain't happening either. So the second derivative is never, ever, no, not ever, equal to 0. And it is undefined when x is equal to 0, just like the first derivative was. So how are we feeling about setting those derivatives equal to 0? Think you're going to be able to do it next week when you have to?
Yeah, for sure. That's definitely going to help out quite a bit.
You can do it. Yes, you can. It just takes practice. Next thing, After you set them equal to 0, the next thing you're going to be asked to do is to figure out when they're positive and negative. So we're going to look at some inequalities here. And we're going to use some of those same functions that we used on the last one. I like this one because, first of all, before you even figure out where it's positive and negative, you need to know what the domain of this thing is, because you can only square root positive stuff. So first thing I'm going to do is figure out where 1 minus x squared is greater than or equal to 0, because we don't care what's happening for x's that aren't in the domain, because we can't use them. So to solve a quadratic inequality, you find the zeros. You plop them down on a little number line. Now, you could do some test points, but really, this is just a sad parabola. You know it's a sad parabola because it has a negative leading coefficient, which gives it a negative attitude. So it's a sad parabola. It crosses the x-axis at plus or minus 1. It looks like that. It's negative, it's positive, it's negative. So we're not going to be able to take the square root over here. We can't take the square root over here. Our domain is only from -1 to 1. So now I want to look at that derivative, and we already calculated it. Y equals -x on top of the square root of 1 minus x squared. I make myself a number line, and since my domain only goes from -1 to 1, my number line only goes from -1 to 1. We had a 0 when x is equal to 0, and we have undefined points at plus or minus 1, which just happens to be the end points this time. So I just plop a 0 in the middle. Now you can do some test points. This one's pretty easy to just logic your way through. Underneath, I put a little row for the sign of y primed. If I plugged -1/2 in here, then I would have a negative of -1/2 gives me a positive thing. Square roots are always positive, so positive. Also, you can think of it as this denominator is always positive. Therefore, the sign of the derivative depends entirely upon the numerator, and the numerator is positive when x is positive, is positive when x is negative, and negative when x is positive. And let's see. Oh no, I don't have the picture on this one. I have the picture on the other one. This one just looks like half of a circle. Looking at the natural log, we had y primed was equal to 2x over x squared plus 5. Another easy one. Just a quick check. What is the domain of the natural log of x squared plus 5? Well, I can only take the natural log of positive stuff, but luckily x squared plus 5 is always positive. So it's all real numbers. So I have to look from -infinity to positive infinity. This has 1 0 when x is equal to 0. So I just divide my number line into 2 halves. And again, you could plug numbers in, but this one's really easy to logic your way through. The denominator is always positive. The numerator is going to be negative when x is negative, and positive when x is positive. So if you were graphing this, you know that your graph is going to be decreasing for numbers less than 0 and increasing for numbers greater than 0. The next one also has a domain that is all real numbers, and the derivative was equal to 0 when x was equal to 6/5, and the derivative was undefined at 0. So we put both of those numbers on our number line, 0 and 6/5. And then I'm going to write down 5x minus 6 over 3x to the 1/3 power. You could pick some points and plug them in, like I did there, or you could just logic your way through it. If you pick a negative number, the numerator is going to be negative. And if you pick a negative number, the denominator will also be negative. A negative over a negative is positive. If you pick something between 0 and 6/5, the denominator is easy. It's going to be positive. But something between 0 and 6/5, you're going to have something like 5 minus 6. You'll have a negative numerator. Negative over positive is negative. And something bigger than 6/5 is going to give you a plus over a plus, which is a plus. Usually you're going to change signs when you get to these, what are called critical values. Not always, but usually. Stop me when you have questions. This one's almost exactly the same. It had zeros at a 0 at 1 and was undefined at 0. And it's the same principle. That denominator depends upon the sign of x. The numerator is going to be negative when x is greater than 1 and positive when x is less than 1. So that'll be the next thing you'll do next week. You'll start by setting those derivatives equal to 0. You'll find out when the functions are increasing and decreasing by looking at this sign chart. And you'll also take that second derivative, plot the zeros and undefined points of that on the number line, come up with pluses and minuses, and you'll determine when it's increasing and concave up like a cup, when it's increasing and concave down like a frown. And you'll be able to know exactly what it looks like, where the maxes and mins are, and you'll be able to draw beautiful pictures. Last thing I was going to do today is just a quick review of writing the equation of a tangent line, because when you get to the section on linearizations, that's really just the equation of a tangent line. So just a quick going over of that. And I know you all just did it. You had a problem on your test where you had to write the equation of a tangent line. This one we have y is equal to the square root of 1 minus x squared. We know what the derivative is because we've done it today, minus x over the square root of 1 minus x squared. We want the tangent line when the slope of the tangent line is 1/2. So that was a weird way to ask that question. I have to take 1/2 and set it equal to the slope. Then I'll cross multiply. So minus 2x is equal to square root of 1 minus x squared. And then I have to think back to pre-calculus algebra. How do I solve such a thing? Oh yeah, I square both sides. So square u, 4x squared equals 1 minus x squared. I'll add x squared to each side. 5x squared equals 1. X squared is equal to 1/5, so x is plus or minus the square root of 1/5. Oh, but when I was teaching 171, I always reminded them that when you square both sides, you introduce extraneous solutions. You have to go back up to the tippy top and see which one or if any of them work. And the only one that works is negative square root of 1/5, because if you put the positive square root over here, positive square root over here, it's not going to work for you because this would be positive and that would be negative. So this is going to be the x value that we need. And what do you need in order to write down the equation of a line? You need a y value, you need a slope, and we have our x value. We have our slope, we need our y value, so we would plug negative 1/5 into y, and we get the square root of 4/5. And then it's just y minus your y coordinate is equal to slope x minus your x coordinate. Easy enough. There's the pretty picture. Then the last one, I ask you to write the equation of the tangent line when the function equals 0. Well, that function equals 0 two places, when x is equal to 0 and when x is equal to 3. It has no derivative when x is equal to 0, so it has no tangent line when x is equal to 0. So you only have to write the equation of the tangent line when x is equal to 3. So you plug 3 in to your derivative to get the slope. You plug 3 in for x to get your y value. You already knew it was 0. You picked it that way. So y is just equal to slope times x minus 3. And there's the pretty picture. Questions on anything?
I don't know if you're allowed to or not, but I had a question on one of the actual text questions yesterday. I don't know if you could just edit the format.
You can ask it, and if I can't answer it, I'll tell you I can't answer it.
Okay. So it was, I think, number 10. And it was essentially the part I got stuck at was it was the same thing. It was write the equation of the tangent line between the 0 and 2 pi, and the equation was, oh god, y equals 4 cosine 3x minus 6 or something like that.
Okay, so this one was not a write the equation of the tangent line problem. This was a determine when the tangent line is horizontal problem.
Yes.
Yeah.
That's what it was.
Yeah. So it's pretty much what we were doing in that whole first bit, taking the derivative and setting it equal to 0.
Right. So I got stuck up on my algebra, and I actually didn't even finish the question. I got I got everything over to the left side, and I set it equal to 0. But when it came to cos 3x, I didn't know how to get the 3 out of the...
Okay, so first off, you're going to take the derivative.
Right.
So you would have y primed is equal to derivative of cosine is negative sine. So it would be negative, and then we have 4 times the derivative of my inside function is going to be 3. And then the derivative of 6x is just 6. So you got something like that for your derivative.
Right.
Okay. Then you set that equal to 0. So you had negative 12 cosine 3x is equal to 6. So you had cosine of 3x is negative 6 over 12, which is negative 1/2.
Right.
Okay. And then you thought about your unit circle.
Right.
And you said, well, I know cosine is 1/2 anywhere that has 3 in the denominator. So it's equal to 1/2 at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And cosine is negative over here.
Right.
Okay, so that means that 3x is equal to 2 pi over 3 plus 2 pi k, or 4 pi over 3 plus 2 pi k. Did you get that far?
No, I don't understand.
You don't know where that came from?
Mm-mm.
You okay to that part?
So I understand the 2 pi over 3. So, but how did you? It didn't make logically. It didn't make sense to me that cos 3x equals negative 1/2, because I don't know. I guess. Huh. I guess that makes sense now looking at it.
Yeah, you have to think way back to trig class.
Yeah.
So you just have to look at cosine. Where is cosine equal to negative 1/2? Well, over here. So that means that whatever we're plugging into the cosine machine, in this case 3x, has to be equal to 2 pi over 3, but it happens again every time we loop around the unit circle. So we add 2 pi k to it.
But if it was from from that problem, it was from 0 to 2 pi, you wouldn't add that at the end, right? You would just leave it.
Well, no, because you got to figure out which ones live between 0 and 2 pi, because this is 3x. You have to divide everybody by 3. So 2 pi over 3 times 3 plus 2/3 pi k. And then you'll do the same thing with 4 pi over 3. So you need to finish by figuring out, well, you know 2 pi over 9 lives between 0 and 2 pi. What if we add 2/3 pi to it? Well, let's see, 2/3 pi is the same thing as 3 over 3, 6 over 9 pi. Now I have a common denominator. 6 plus 2 would be 8 pi over 9. Yeah, that's between 0 and 2 pi. That's an answer. What if I do it again? 8 plus 6 gives me 14 pi over 9. Is that between 0 and 2 pi? Yeah, it is, because 2 pi would be 18 pi. So that's a good answer. Let's try it again. 6 plus 14, 20 pi over 9? No, I can stop.
Wow.
Those are 3 of the answers. And you're going to get
close.
3 more, because you have 3 cosine of 3x in here. That means you're going to get 3 answers for each of these.
Wow. Is that kind of across the board for if it was from 2 pi?
Yeah.
So if it was like 6x, it would be 6 answers?
Yep.
Wow.
Yep.
I never knew
Because
that.
remember, that's the period of cosine. It makes a complete circuit from 0 to 2 pi. And if you multiply it by 3, it's going to do that 3 times.
Right.
If you multiply it by 6, it's going to do that 6 times.
Right. Okay. Yeah. Oh, wow.
So there you go. We did a couple of those trig functions a couple of weeks ago here in the boot camp.
I think I was here for them, but my memory is very bad.
Yeah, it's a lot. I know it is. Any other questions? I'm going to turn off the recording. I probably should have turned it off before I answered that question.